Okay. So I've only got less than an hour today to continue our discussion of the OLG model. I think this is where we left off in the last class. So on the left-hand side of this piece of paper here are the 4 key equations of the basic OLG model without Social Security, right? In the last class, hopefully what I was able to do was solve for the consumption Euler equation in the model that had pay-as-you-go or unfunded Social Security. You see it looks very similar, except the return to Social Security is given by 1 plus n, right? Since the population grows, every dollar that is paid into Social Security by the young gets paid out one plus n dollars to each old individual at time t. The capital accumulation equation, or the savings locus, that's going to be the same as the original model without Social Security. I'm sorry, I wrote this down wrong. So this is this is what the model without Social Security looks like, right? Notice that the savings locus looks exactly the same. That should be, now we could have derived this. I'm going to let you guys do that. It was derived by appealing to this equation, right? Aggregate output is consumption plus investment. If you plug in the resource or the identity for investment, you can play around with that equation and derive capital per worker as a function of current savings, okay? In a model with pay-as-you-go Social Security, why is KT plus 1 equal to just S instead of S plus D? Because our Social Security taxes don't get used to purchase capital. They're transferred immediately to the old generation, right? And so the capital accumulation then is determined only by the private savings of the young. And so that equation is actually identical to the model that doesn't have Social Security at all. And then of course the other efficiency conditions are the same as well for the real wage and the real return to capital. So the only real difference is in this consumption Euler equation. But you can see here that unlike the fully funded Social Security system, where you had everywhere you had an S over here, you had an S plus D over here. And so the two models have the same allocations because Social Security has the same return as private saving, right? If the government takes your Social Security payments and invests it in the capital stock, then that world is going to have the same allocations as a world without Social Security at all. But in this unfunded system, however, there's going to be a difference between those two because the return to Social Security is no longer necessarily equal to the return to private savings. N is not necessarily equal to R. In fact, what we care about are these situations where N is actually bigger than R. That is a dynamically inefficient economy. Before we get to the 5th proposition, and we try to prove that, and I'll run out of time doing that, I'm 100% sure. Let's see how an increase in Social Security in this pay-as-you-go or unfunded system affects the private savings decision. So that is, what is the partial of S with respect to D equal to in an unfunded pay-as-you-go system? Now let me make an assumption here. To keep the math as simple and as clean as possible, I'm going to assume that all generations get treated equally. So dt is going to be equal to dt plus 1 is equal to some just constant D. So Social Security taxes are the same lump sum every year, which implies then that the benefit that you get from Social Security is just equal to 1 plus N times D. All right, how do we find this partial derivative? You guys should be comfortable with how to do that by now. We simply apply the implicit function theorem to the first order condition, right? So that would be what? Negative U double prime C1t times the partial of S with respect to D minus 1 is equal to beta 1 plus R U double prime of C2t plus 1 times 1 plus R t plus 1 partial of S with respect to D plus 1 plus N. Now, I'll let you guys do the math, but if you rearrange the terms and solve this for ds dd, you get negative U double prime of C1 plus beta 1 plus R times 1 plus N times U double prime of C2 t plus 1. That whole thing divided by U double prime of C1 plus beta times 1 plus R squared times U double prime of C2. The utility function's concave, so the second derivatives are negative. So you have a negative over a negative is a positive times a negative. So we know that this is going to be less than 0. The question is, how much less than 0? In the world with a fully funded Social Security system, a $1 increase in Social Security lowered your private savings by exactly $1, right? Because Social Security and private saving were perfect substitutes. That is no longer the case in this model. Why? Because the return to Social Security can be different than the return to private saving. There are 3 cases we need to think about here. Case 1. Notice that the partial of saving with respect to D in absolute value can be less than 1 if N is less than RT plus 1. The only difference between the numerator and the denominator here is a 1 plus N over a 1 plus R, right? The rest of it is the same. U double prime C1, beta 1 plus R, there's a beta 1 plus R, U double prime of C2. The only difference is there's a 1 plus N on the top and an extra 1 plus R on the bottom. Well, if N is less than R, then this ratio is less than 1 at absolute value, meaning that a $1 increase in Social Security lowers private savings by less than $1. You get $1 more in Social Security, you might save less by 90 cents. Now, why is that? It's because the return to private saving is higher than the return to Social Security. So just because you get $1 more in Social Security doesn't mean you're going to save by $1 less, because the return to private savings is more attractive. This this comparative static is equal to 1 if N is equal to RT plus 1. Now we have a situation that is basically observationally equivalent to a fully funded system, right? If N is equal to R, then the numerator and the denominator are exactly the same. And a $1 increase in Social Security would simply then reduce private savings by $1. But what if N is greater than RT plus 1? Now, in that case, DSDD is greater than 1 in absolute value. A dollar increase in Social Security lowers private saving more than a dollar. Why? Because the return to Social Security is more attractive than the return to private savings. In other words, there's an income effect here that if we're paying a dollar more into Social Security, we can get just as much consumption in the next period by saving even less than a dollar today, because the returns to Social Security dominate the returns to private savings. This is the case that we are interested in, because this is the case in which the steady state is dynamically inefficient, where capital and savings have accumulated to the point where the capital stock exceeds the golden rule. Okay, y'all have any questions about that so far? Does that make sense? You guys see the fundamental difference between these two tax and transfer systems? In a fully funded system, where the government takes your taxes and saves it in the form of capital investment, then there really should be no difference between the government saving for us or us engaging in private saving. And allocations would be the same as a decentralized competitive world without a government at all. Okay, so if we're already over accumulating capital, then we're going to continue to over accumulate capital in that fully funded world. In a pay-as-you-go tax and transfer system, things are not as easy, right? They're not as clean, because in general, the returns to Social Security given by the population growth rate will not be the same as the return to private saving, that is the return to capital. When the former exceeds the latter in a dynamically inefficient world, then more Social Security is going to reduce private savings more than 1-to-1.
So what are people doing with their money and just holding on to it?
They're getting taxed.
And like you said, they're like,
yeah, no, if you rate, the budget constraint is still going to be satisfied. If I tax you an extra dollar, then what you'll do is you'll reduce your savings by, so what that tightens your budget constraint, right? But what you'll end up doing then is reducing your private savings by, let's say, $1.25. So what do you do with that extra 25 cents? You consume it, right? So your consumption is going to go up because of that income effect. But in every period, you're still going to satisfy your budget constraint. Okay, the last thing I want to accomplish, and it looks like I'm going to have to do this I won't get through all of it today, because the proof is a little complicated, and there's value to doing this proof because some of the tricks that are utilized will help you solve other problems that you see in macros. So I actually want to go through the steps of the proof for you, because it's not obvious how all this stuff is done. Let me just read prop 5, and then we'll try to sketch through a proof and get through as much of it as we can today. If I have to use I may come in here on another day and record the rest of that proof and just post it online. You guys can either zoom in and watch it, or if you want to show up, you can. Okay. Okay. Prop 5, consider a basic OLG model in which the government operates a pay-as-you-go Social Security system. In an unfunded system, the government collects D from the young and redistributes it to the current old generation with per capita transfer 1 + N times D. We've covered all that. Moreover, suppose that the decentralized competitive equilibrium without Social Security is dynamically inefficient. So we're in this world where the steady state return to capital is less than the population growth rate. That's the relevant starting point or comparison point for us. If all of that stuff is true, then what Proposition 5 says is that there exists a feasible sequence of Social Security payments that leads to a competitive equilibrium starting from date T that Pareto dominates the competitive equilibrium without Social Security. So if we're in a dynamically inefficient world, then we can design a pay-as-you-go tax and transfer scheme that will actually benefit not only current generations, but all future generations. Now, what does that sound to me? That sounds to me like what we looked at a couple of class periods ago, right? We looked at a simple OLG model, and from the perspective of a benevolent social planner, what did we do? We did a proof of a proposition that shows if you reallocate capital over time, if you lower the capital stock just a little bit, that increases the consumption not only of today's generations, but all future generations as well. If you understood that intuition, this makes perfect sense. What's the difference between that setup and this one? Here, we're not going to assume this silly benevolent social planner construct, but rather we're going to try to engineer or implement what a social planner would do using fiscal policy as the right institution. In a purely competitive, decentralized world, in other words, can we implement what a social planner would be able to do through an appropriate tax and transfer scheme? The answer to that question is yes, okay? But we need to prove it. So hopefully you understand that this proof is why this proof is going to be positive, that you can indeed arrange or set up a transfer scheme that is going to end up making everybody better off because we're starting in this dynamically inefficient world. Can we use the tax system to achieve what the social planner did 2 class periods ago? That is, reduce the capital stock and therefore boost everyone's consumption. You guys see what I'm kind of talking about there? Okay, let's start to work through the key parts of this proof together then. To do this, I'm going to have to set up define some concepts. Okay, let me define the following. So C1, C2, S, K, R, and W. This sequence of variables corresponds to the equilibrium. So this is the equilibrium of an unfunded system, pay-as-you-go system. One in which, in particular, the Social Security tax every period is just some fixed value, let's call it D bar, for all T. And therefore, the Social Security benefit every period is just 1 plus N times D bar. Okay, what this proposition claims is that there exists some D bar that can even be sufficiently small, such that the equilibrium that we describe here is a Pareto improvement over the fully decentralized equilibrium of the model without Social Security at all, as long as that equilibrium is one in which R star is less than N. In other words, it's dynamically inefficient. So again, to fix concepts, let me define the following: C1 star, C2 star, S star, K star, R star, W star. This is the steady state of the decentralized model without Social Security. Okay, I'm just kind of defining the notation so we're not confused here. In other words, what we need to be able to do is compare outcomes really in these 2 different worlds, the model with Social Security and the one without it. So this allocation here, C star through W star, would be the steady state of the model that doesn't have any Social Security. In other words, it's the steady state of this unfunded system where D bar gets arbitrarily close to 0. You guys see what I'm talking about here? Okay, this proof has a couple of steps. Each step is a bit involved. In step 1, I want to show that there exists a sufficiently small D bar, that is Social Security payment system, such that the steady state capital to labor ratio in the economy with Social Security, I'm going to denote that K bar. So this is the steady state with Social Security, is somewhere between the golden rule steady state and the steady state without Social Security. And that KT will converge down monotonically towards K bar, where initial capital we'll assume is the steady state of the economy without Social Security. Okay, so what does all that math say? Imagine that we start, our initial period is this economy. We are in the balanced growth path and in the steady state of the competitive model without any Social Security at all. I want to do the following thought experiment. What if we at date T, or at date 0, implement a very small pay-as-you-go Social Security scheme? What I'm telling you then is that the new steady state capital stock associated with that change, K bar, should be less than the previous steady state, but higher than the golden rule. And that the capital stock will converge monotonically towards that new steady state. That's step 1. Step 2 will then be showing that the allocations that come in this new steady state Pareto dominate the ones that were in the previous steady state. The way we're going to do that is we're going to show that the allocations here in the previous world without Social Security are always going to lie inside of the budget set faced by an agent who lives in the world with Social Security. Therefore, they can increase their welfare by consuming more and moving out towards their budget set. That's going to be step 2, though. We may not get to that until the next class. Okay. Any questions so far conceptually about what we're doing? Look, it's more important to me that you guys kind of understand conceptually what's going on here than be able to fly through every line of math. The derivatives are straightforward, and once you look at it a few times and you move stuff around, you'll see what happens. But I want you guys to understand, what it is we're doing. We're starting from a world without Social Security. We're in the steady state. We're now going to implement a sufficiently small tax and transfer scheme, a D bar that's just a little bit above 0. The first thing we want to do is show that that leads to a new steady state capital that gets us towards the golden rule, but not all the way there. Tavoy?
Oh yeah, that's what I was going to ask. If we actually reach K goal with that first change.
Well, no, we'll reach K bar in the long run, right? There's going to be some transition period from K star to K bar. But what I want to show is that in fact, the capital stock will start to decrease once we start this Social Security plan. Okay, so how do we do this? What we need to do is we need to show that increasing D bar in the neighborhood of 0 actually is going to reduce private savings, first of all. But that is only a partial equilibrium result. Ultimately, we need to show how it affects the entire capital savings locus, right? That is that mapping from KT to KT plus 1. All right, so remember the first order condition of this model reads as follows. U prime of C1, which is WT minus ST plus D bar here, because Social Security is constant, is equal to beta 1 plus R T plus 1 times U prime of C2T, which is 1 plus R T plus 1 ST plus 1 plus N D bar. Okay. By the implicit function theorem, we know that there is some private savings decision that would be a function of the wage, the return to capital, as well as the Social Security payment. What I want to do is I want to, so let's be careful about this. I want to look at how savings changes for a unit increase in D bar, but in a neighborhood of D bar close to 0. So we're starting at this competitive model without Social Security. I want to analyze a marginal incremental increase then in Social Security. How does that affect the private savings locus? So we want to take derivatives through the Euler equation, but then evaluate that in a neighborhood of the no Social Security economy. That is in a neighborhood of D is equal to 0. All right. So this derivative problem is just like the one we did on the last page, right? We have, let's see, we want to, essentially what I want to do is find this. What is the partial of savings with respect to Social Security in a neighborhood then of the competitive model without Social Security? This partial derivative is what I'm trying to figure out. Okay, so let's take derivatives through the first order condition here. It's going to be U double prime of C1 star times negative S sub D bar evaluated at W star, R star, and 0. Remember, we're in a neighborhood of the no Social Security equilibrium. Minus 1 is equal to beta 1 plus R star U double prime of C2 star times 1 plus R star S sub D evaluated at W, R, and at 0, plus 1 plus N. So it's the same problem that we analyzed on the previous page. Therefore, the derivative of savings with respect to the Social Security payment in a neighborhood of 0 Social Security should be equal to negative U double prime of C1 star plus beta 1 plus R star times 1 plus N U double prime of C2 star, all of that divided by the same thing except with a 1 plus R squared. Which we know is less than negative 1 because R star is less than N, right? So in a neighborhood of the 0 Social Security equilibrium, the first penny of Social Security taxes that we pay is going to reduce our private savings by more than a penny. Now, unfortunately, this is only a partial equilibrium result. You guys know what I mean by that? In macroeconomics, we're really concerned about general equilibrium effects, not just partial equilibrium effects. If you lower private savings, that is, you invest less in capital, there's probably that's going to put downward pressure on the capital stock, right? That's a partial equilibrium effect. What are the general equilibrium effects? Well, what does lower capital do? Lower capital lowers the marginal product of labor, and therefore it lowers the real wage. See, this is where macro gets hard, but interesting. What happens if you face lower real wages because of declining capital? You're going to save less. That tightens your budget constraint. You're going to consume less and save less. So less savings goes down directly because of the increase in Social Security. It goes down indirectly again because it's going to lead to lower wages. But lower capital does what to the returns to capital? That is, remember, the return to capital is equal to the marginal product of capital. As the capital stock declines, what happens to the marginal product of capital? It goes up, right? The slope of the production function gets steeper. As the returns to capital go up, your income is going to rise in the second period of your life. That's going to have an impact on your potential savings in the first period, which is going to be ambiguous depending on if those income or substitution effects dominate. So it's not clear that Social Security is necessarily going to lower the capital stock here, because it has these general equilibrium effects that work through the returns to capital. We actually need to analyze the general equilibrium effects of an increase in Social Security. Okay, well, how do we do that? Well, we need to look directly at, we're going to use this result, by the way. I didn't do it just for nothing. We need to look directly at the key equation in our model, which is the aggregate savings locus, or what we call the law of motion for capital. That was the second equation in our model. KT plus 1 times 1 plus N was equal to what? It was equal to ST, private savings, where private savings is a function of the real wage, which in general equilibrium is equal to the marginal product of labor, F minus K times F prime of K. It's a function of the real return to capital in period T plus 1, which is the marginal product of capital in period T plus 1 minus depreciation. And it's also a function of the Social Security payment, D bar. Now look, this law of motion for capital cannot be solved explicitly for KT plus 1. Why? Because we have KT plus 1 on the right-hand side of the equation. We can't solve for a fundamental law of motion like we can in the Solow model. But we do know that there exists some mapping, let's call it G, which tells us how KT, as well as whatever the Social Security payment is, determines what tomorrow's capital stock is going to be, right? In other words, the implicit function theorem here suggests that there's some mapping, let's call it G, that we can define implicitly that tells us how KT maps into KT plus 1. That is the kind of implicit solution to this law of motion for the capital stock. Right, if I were to draw what this function G looks like, it probably looks something like this. It's a function that maps KTs into KT plus 1s, and it almost certainly has this kind of concave shape to it. Right? Where would the steady state value of capital be located? Wherever the 45-degree line intersects that mapping G. Right? Actually, let me draw the first G where Social Security is 0, so that the steady state capital I'm talking about is indeed K star, as I defined it above. Here's what we want to show. We want to show that raising Social Security is going to shift down this G function or G mapping like this to a new steady state value of capital, call it K bar, that is still greater than the golden rule level of capital. Unfortunately, just doing the derivatives on the savings schedule like we did ago is not sufficient, right? We need to take a look at the entire law of motion for capital. All right, in other words, this is the object we want to find. What is the derivative of G with respect to Social Security in a neighborhood of the equilibrium without Social Security? Can we be sure that G actually shifts down here so that the steady state value of capital stock declines? That's the object we're looking for. Okay, well, we can do that. Let's take the derivative then of this equation with respect to D. Now let's be careful about where D shows up, okay? This G function needs to be substituted into the above equation anywhere you see KT plus 1. Here, as well as here, so that we can take derivatives appropriately. So then what would be the derivative with respect to D? Well, it would be G sub D.
Can you shift down?
Oops.
Thank you.
Now, again, we're evaluating in the no Social Security equilibrium. So evaluated at K star and 0 times 1 plus N is equal to, I'm going to move back and forth, Richard, so just bear with me. Where does D show up in the right-hand side of the above equation? It's not part of the real wage, but it is part of RT plus 1 as well as the third argument. So it would be S sub R evaluated at W star, R star, and 0 times the derivative of R with respect to D. Well, now we're getting a little tricky. That would be F double prime of K star times, let's see, this is a KT plus 1, right? So it's times G sub D evaluated at K star and 0. Got to use the chain rule right. Plus, don't forget this last D argument, S sub D bar evaluated at W star, R star, and 0. That's why we did this derivative on the previous page. That's where we're going to need it again. Now, if I solve this equation for G sub D, what do I get? I get S sub D divided by 1 plus N minus S sub R, W star, R star, 0. Okay? So that's not too difficult. You can take those partial derivatives. The question is, can we sign this? What's the sign of the numerator? Well, we know that. It's negative. We got that on the last page. Okay, in fact, it's less than -1. What about the denominator? 1 plus n is positive. What's S sub r? Well, we don't know, right? Savings could go up or down depending on whether or not income or substitution effects dominate. And so actually, we don't know what the sign of the bottom is. So the whole thing is still ambiguous. We're going to need to do a little bit more work to figure out what the sign of this thing is. Well, can we appeal to some other information to do that? I'm going to say yes. So here's the way I'm going to approach this. This is the way we would like the mapping from KT to KT plus 1 to look, right? So we think that this G mapping crosses the 45-degree line at a slope of less than 1 with this type of concave shape to it. What does that accomplish? That accomplishes two things. It guarantees that there's a unique steady state, and it guarantees that that steady state, if it intersects the 45-degree line at a slope of less than 1, is globally stable, right? Now, what did we learn several days ago? The OLG model with CRRA preferences and Cobb-Douglas utility, Cobb-Douglas production, has a unique steady state and is globally asymptotically stable. So this G mapping from KT to KT plus 1 looks kind of like this. Well, what does that imply then? That there should be stable monotonic convergence to the steady state, right? You're not going to have this kind of oscillatory dynamics to it. In other words, the slope of the G function in the neighborhood of the steady state should be what? A positive fraction, right? Stable, unique equilibrium implies the following: that the slope of the mapping G, that is the derivative with respect to K, in a neighborhood of the steady state is a positive fraction, right? This we know, assuming the model has CRRA preferences and Cobb-Douglas production. Can we appeal to this information to help us sign the denominator up here? Well, I think we can. What we have to do then is go back and take the derivative of this equation again, but this time with respect to KT rather than D, and see what we get. All right, so what's that going to look like? Well, you would have a G sub K, K star 0 times 1 plus N would be equal to, well, you've got KTs all over the place on the right-hand side. So it's S sub W, W star R star 0, times the derivative of W with respect to K. Okay, well, that's going to be F prime of K star minus F prime of K star minus K star F double prime of K star. These F primes are going to cancel there. Plus, let's see, S sub R, W star R star 0 times F double prime of K star. And since that's a KT plus 1 in that argument, it would be G sub K, K star 0. Now what we want to do is group terms and solve for G sub K. If you rearrange that equation, what you're going to find is that the partial of G with respect to K is equal to negative S sub W times K star F double prime divided by 1 plus n minus s sub r. W star R star 0. Okay, I made a mistake a minute ago that you all did not catch. Shame on you. And this G sub D attached to this S sub R is a F double prime of K star. The denominator is still ambiguous though, even though F double prime is negative because we don't know the sign of S sub R. But what do you notice here about this derivative, G sub K? It has the same denominator as G sub D, right? Now, what's the sign of the numerator here? Savings goes up as your wage increases. That we know. F double prime is negative, so that's a negative, positive, positive, negative. It makes the whole numerator positive. The only way for the slope of G to be between 0 and 1 then is if the denominator is also positive. It can't be negative. That's the only way for this thing to be between 0 and 1. That is for this model to have stable, non-oscillatory dynamics. So if we make that assumption that the G mapping looks like this, then that is enough to conclude that 1 plus n minus S sub R times F double prime is going to be positive. That implies then that G sub D, K star 0, is going to be a negative over a positive, making the whole thing less than 0. And indeed then, the G locus, or the G mapping from KT to KT plus 1 shifts down as the Social Security payment increases, leading to a lower steady state value of capital. You guys see how I did that? Okay, so this is the law of motion for capital in the OLG model with Social Security, right? KT plus 1 times 1 plus n is equal to private savings. Savings depends on the wage, the return to capital, and D. The thing we want to try to determine is whether or not steady state capital declines as we increase D. Now, unfortunately, we can't solve this Tavoy for KT plus 1, but we know implicitly there's a mapping G that tells us how KT along with D determine KT plus 1. It's defined implicitly by this equation, and it looks like this over here. What we are postulating is that an increase in D is going to shift that mapping down, resulting in a lower steady state value of capital. But we have to prove that. So the first thing we did was we wanted to find the derivative of G with respect to D by taking the derivative through this equation with respect to D. And this is what we got. Unfortunately, we couldn't sign that because we didn't know the sign of the denominator. How do we sign the denominator? Well, we appeal to other information we know is true in the model. And that is that the steady state is unique and has monotonic convergence. That means the G mapping has to slice the 45-degree line at a slope of less than 1, right? That means the derivative of G with respect to K, not D, that's the slope of G here in KT plus 1 space, has to be between 0 and 1 in a neighborhood of the steady state. Well, let's calculate what that derivative is by taking the derivative of G with respect to K through this law of motion. That's what I did in this second step here. Right? You do the derivatives carefully, you rearrange the equation, and you get this. And you see that in the denominator, you have the same term that we did here, where we were taking the derivative of G with respect to D. However, we know that the denominator here has to be positive because the numerator is also positive. So the only way we can make G sub K a positive fraction, and we know that it has to be true, is if the denominator is also positive. Now that we know the denominator here is positive, we can go back up here and actually sign what this derivative is. It's a negative over a positive, making the whole thing less than 0. Therefore, G indeed shifts down as Social Security taxes go up. That is the general equilibrium result. It's much more challenging to do because we have to consider how Social Security works, not just through private saving, but how that private saving channel affects the capital stock and therefore affects the real wage and the return to capital. So higher Social Security is essentially lowering the capital stock for 2 reasons in this model, right? One is that it immediately tightens the budget constraint, right? Nathan, if I'm Uncle Sam and I'm gonna raise your Social Security tax, you immediately have to use more of your income to pay Social Security, which means you immediately have less of your income to save. So savings goes down, the capital stock goes down. That's the first channel. But there's also an income effect that's going on. You now know that your return to that Social Security is going to be higher than what you would be able to get on your own private savings, because N is bigger than R in a dynamically inefficient world. So you're not just going to lower your private saving by $1. If I tax you more, $1 more, you're going to lower your private savings by $1.50, right? And therefore consume 50 cents extra. And so private savings falls even more than dollar for dollar because we're substituting away from private savings into Social Security. There's an income effect that's going on there. Social Security is going to provide you with greater returns, and so you can consume the same amount now in your old age by saving even less while you're young. That's the general equilibrium income effect here. Those two things combined are what give rise to this downward shift in this G mapping, and ensures then that the capital stock will decline monotonically towards a new steady state that is closer to the golden rule. That's step 1 of the proof. Step 2 of the proof, which I don't have time to do, but I'll write down what that step is, and we'll do it next time. Is to show that the welfare of all generations including during the transition to the new steady state, increases as Social Security goes up. So all agents are better off. Now, here is the general way in which I'm going to try to prove this. I want to show that this consumption allocation, so this is what we would have consumed in a world without Social Security at all. I want to show that this consumption allocation lies inside the budget set of all future agents who face a world with positive Social Security. So let's define those folks' consumption allocation as C1T C2 T plus 1. I want to show that that consumption allocation strictly dominates C1 star, C2 star for all T. And we do that by showing that the consumption allocation without Social Security is going to lie inside the budget set of all future agents who do face Social Security. If that's the case, then what are those agents going to do? They would simply, they have unused resources, right? They would be able to spend those resources and move all the way out to their budget set and thereby consume higher quantities over their lifetime. In that way, we show that the allocations with Social Security would Pareto dominate the ones without. That's the second step. Now, that should be intuitively obvious to you because in the last class, or maybe it was the one before, we basically argued the same thing, but from the construct or in the context of a benevolent central planner type argument or framework, right? Here, we don't have a benevolent central planner. We have a decentralized economy, but there is a fiscal policymaker. And the idea here is that you can design a appropriate tax and transfer scheme that does essentially the same thing as what a benevolent planner would do. Lower the capital stock, rearrange resources intertemporally in a way that makes everyone better off. We know that holds in the central planner world. It should hold in this world as well. The way we're going to prove it, however, is a little bit different by showing that this allocation lies inside of the budget set faced by these guys here. I don't think that should take me more than about 30 minutes. So what I think I'm going to have to do then is perhaps on Friday, I'm just going to come in here and record the last part of this and post it. I'll let you guys know what time I'll do that. If you want to show up, you don't have to, or if you want to log into Zoom to watch it. But I really would like to, on next Monday, to be able to start with a clean slate on dynamic programming, because I think I've fallen behind this semester, given all of this stuff, along with, I think I'm a little bit quicker at writing the stuff on the board than I am on paper. And so I just want to make sure I don't fall too far behind, okay? But it shouldn't be too much of a hardship because whatever I'm not able to do, I'll be sure to record it and post it. Okay, y'all have any questions then?